All right. Good morning, everyone. How are you doing? Good morning.
Good morning, sir.
Right. All right. I think I have given you all enough time. No, well, not you, but the others enough time to come on in. Um, I had a side chat with a student just to remind me exactly where we are. Considering all things, we're not moving badly, but we're slightly behind. Um, I think that week when I gave you the mock mid-semester would have ate up some of our time, so we have to find some other time to meet. But today is going to be a rough class, and I say rough because I want to recognize much is going to be required of you. So I have 3 units to finish off with you guys. I have integration that I need to start today and hopefully finish today. I have cost function to do with you, which is what I wanted to have done last week. I have stationary points again to do with you, but this time it's going to be of a multivariable function. And yeah, and that's it. The double integration can take place right here. So I have those 3 areas to cover. And 3 areas to cover, and we have two more classes left. I should be able to do it if we commit ourselves to it, all right? So I just want to pick up the big man upstairs, thanking him for life, thanking him for waking us safely. Could not have done it without him. Whether or not you have dinner for today, that's none of your business, nor my business. That's his business. He will now know that him picking them down a yard, not fit and will provide. So let us just depend on him, and as we are about to begin our class, let us depend on him for the added wisdom, knowledge, and understanding that is going to be so required to understand what is happening here. All right, so let's go. Good morning to you, to CAPE students. This should be an easier class for you because you would have seen a piece of the integration already, but you are on the same learning curve as for the business gap for students. Now, as I said before, I'm going to ask for your indulgence. I'm not going to be able to do integration today and come back next week on integration. I have to finish integration today. As a matter of fact, I want to finish integration today. And if it means that I can finish integration in about 3 hours, and there is a small topic that I could start and finish that includes both integration and differentiation, or I can go through the multivariable function with you, all right? But whichever it is, I'm finishing integration today. So I'm going to ask you to just be around with me. And let us see how much we can cover. Let's go. So we're talking about the rules of integration now. CAPE students, looking at this document, I now remember that I had promised to send it off to you, and I didn't send it off. Did I send this, CAPE students, this document that I'm looking at here?
No, sir.
Right. I remember when I met with you face to face in after bio class one morning. I don't know if you remember that morning when you had your Caribbean Studies exam. I had promised to send it off. Now that I'm looking at it, I remember, but I didn't. Sorry about that. All right, so let's go. Rules for integration. The following rules for definite integrals are obtained by reversing the corresponding rules for differentiation. So what I'm saying to you here is the opposite of differentiation is integration. The opposite of integration is differentiation, right? So one is the reverse of the other. Their accuracy is easily checked by taking the derivative of the antiderivative. So the antiderivative is also called the integral. So another name for integral will be antiderivative, all right? To be sure, this equals to the integrand. The integrand is what it is that you are going to be differentiating, which will be the differential, all right? So there are some rules. There are some rules to follow. You know, when I did indices and logarithms with you CAPE students, and I didn't teach you pre-calculus, business calculus students, but whoever taught you would have taken you through several rules of indices. And they would have also taken you through several rules of logarithms, about 4 of them. And those rules are rules that should guide you. When you look at the stuff, you say, oh, is this rule I have to use? When I'm adding, I'm going to multiply. When I'm subtracting, I'm going to divide, right? So let us go. It says the integral of a constant k is going to be kc, not the other school that is on North Street. There's just really one school on North Street, and it's on the right-hand side, right? And don't ask me when in which direction, because there's still just one school. So whichever direction you go, there's just one right-hand side on North Street, right? So it's not that school that I'm talking about now with the k and the x right there, so the c also. So my c is known as a constant of integration. My c is known as a constant of integration. Now, whenever I'm integrating an indefinite integral is going to be the constants of integration. Let me pause. One of the things that I keep saying to students, when I'm going, and I don't know if it happens to you or if it's just me alone, please tell me that it happens to you so that I know I have company. When you're going somewhere that you don't know where you're going, and you have to follow a direction or follow Google Maps, don't it seem longer than when you're coming back?
Yes, sir.
You know, see, your driver said, John, what's so far right there? And then when you come back, it's about, hold on, it's not so far, because on your route, you start thinking about, oh Lord, the topic we start with is difficult, and you put some blockage right there. And the blockage that you put right there now is not speeding up the process for which you're understanding, right? But when you get it, it's about, hold on, it's not really that bad, and then you start liking the topic, right? So you may hear somebody say, you can't go and go to maths. We can't start my associate degree because maths in there never fail it. So it makes sense to start the something. Start the something. So let's go. So the integral of a constant k is going to be kx. Because when I integrate a constant, I'm going to pick up the variable. So when I integrate a constant, I'm going to get kx. And I'm integrating this constant with respect to x. Oh, so that's what dx means, sir. Yes. Dx means that I'm integrating with respect to x. Then, sir, what if I had dp? Then this would have been kp. What if I had dr? This would have been kr. Because this tells me what I'm integrating with respect to. All right? dz, kz. It means that I'll be differentiating. I'll be integrating with respect to c. All right? And I have my plus c because whenever you are integrating an indefinite integral, you must have your constant of integration every single time. All right? So that's rule number 1. Rule number 2, the integral of 1 written simply as dx, not 1 dx, it's just dx. So when you integrate in 1, you're not going to write 1 dx, you're just going to write dx, and the integral of dx is just going to be c, x plus c. It's going to be x plus c. Let me just say something to you. When you have, you know how to differentiate that, dot differentiation. When you have, for example, 2x, when you differentiate 2x, what will you get?
2.
2. See there? Like the constant 2. So this is what we are saying to you. By reversing so when you do the reverse the corresponding rule of differentiation, you'll obtain the other one. So it says that the accuracy is easily checked by taking the derivative of the antiderivative or the integral. So if you want to know you're right, just differentiate the function when you get the answer, and you can check. When you differentiate x, what you get? When you differentiate x, what you get? Class, when you differentiate x, what do you get?
1.
1. See there? You get 1. So if from this elongated s, it's an elongated s. This elongated s is telling that you're differentiating. Your results over here, when you differentiate over here, you get this. When you integrate this, you get that. Differentiate this, you get that. So integral, differential, integral, differential, differential, integral, differential, integral. All right, let's go this one here. This one here is the most used of the three. It has the rules for integration, and it says the integral of a power function x to n, where n is not equals to 1, or to negative 1, sorry, where n is not equals to negative 1, is going to be where you add 1 to the power and divide by the new power. You're adding 1 to the power and dividing by the new power every single time. So x to n dx, I'm integrating x with respect to, sorry, I'm integrating x to the n with respect to x. I'm adding 1 to the power, so it becomes x to the n plus 1, and then I'm dividing by the new power, which is n plus 1, n plus 1, and I have my plus c. Here is an indefinite integral. Why is it called an indefinite integral? So if you have indefinite integral, that means you have a definite integral too. Absolutely. It's called indefinite because I do not have an upper limit and a lower limit. Let me stop and say something to you again. So you know, one of the things that I love about the United States, I mean, there are many things that I love about the United States of America, if I were to be honest, is, you know, sometimes you have to find somewhere and you use Google Maps and you meet to an intersection and Google Maps is supposed to be on Mountain View Avenue, but you do the intersection, you look up and you can't see no sign and say Mountain View Avenue because the sign is gone. For the owner come take off the sign, and sometimes you wonder which road we on. Sometimes I drive a road and I say which road is, and I'm looking at business places with their addresses up or the names up, and there's no address to even remind me which road I'm on. Them things are not foreign. Them things are not foreign, you know. You have something giving somebody direction to come to your house. You said, no man, come on 7th Avenue, 199th Street and Love Lane. Okay, you reach 7th Avenue. And when you reach 7th Avenue, you can go into 7th Avenue and you can look for 199 and Love Lane. All right, now you find 199 and Love Lane. Where to go? They say, all right, it is 740. Then you start looking for 740. All right, what's the point? When you have an indefinite integral, all I'm telling you is just 199 and Love Lane. So you're on the road we're living in, but we don't know which are the house. You don't know which house, but you know you're on the road. So that's an indefinite integral. The definite integral will tell you exactly where the house is. Exactly where the house is. All right. One of the other things I like about the US is when you go like for Amazon for argument's sake, it happens with eBay too. When you go to Amazon to purchase some stuff, and I'm putting in my fam's address and say I forget the zip code is over 5 digits, and I mean they have additional digits that they use to locate the building and rate it and support and so on. Sorry. If the address is incorrectly inputted, or while I'm typing the address, there are several suggestions that will come up. Several suggestions that will come up because it is built into their system. So you can't technically make a mistake with your people's address unless you can send it back to somebody else because it comes right up. So that's one of the things that I love. And how I relate it to the integration here, definite integral and indefinite integral. The indefinite integral would be me find your avenue is a very long avenue. Or you live on our road, off our road. But it's a very long road. Still, for example, you go off Mountain View Avenue. The whole long Mountain View Avenue. And I say, sir, just up to Mountain View Avenue. And that's where I live. Okay. Where you live from the top of KFC right up there, so with Old Oak Road, or you go all the way down to Windward Road. It's a long stretch. That's indefinite. So that's why I have to put my concept of integration to tell us, say, we don't know what I see. It can be anything. If, on the other hand, I say to you that I've had 137 Mountain View Avenue, nowhere else matters on Mountain View but the address of the ECC. Nowhere else matters but the address of the ECC. That's the only one I have. Why, sir? Because it now becomes a definite integral. I am definitely going over to Excel from college. I'm definitely related to 137 Mountain View Avenue for 4 years. 2 years from my associates, 2 years from my bachelor's, and for the Cape students for 2 years. All right. So remember that. So if you've been an indefinite integral, meaning you don't have an upper limit or a lower limit, if you don't have your constant of integration, the question is not correct. All right. So remember now, what we're doing, we're adding 1 to the power, and we're dividing by the power. So long I'm staying at this one, there's a reason why rule number 3 is highlighted. There's a reason why rule number 3 is highlighted. Because that rule is what I'm going to be using more than any of the other rules. All right, let's go. I hope it's clear so far.
Yes, sir.
Good job. All right, now I did say to you that n cannot be equal to -1. Can you look at the formulation in purple and tell me why n cannot be equal to -1? Can somebody look at it and tell me why n cannot be equal to -1, please? Talk to me, man. Remember, we have a lot to do today. Anybody, keep our reason.
Really, rules for your reference, sir?
No, rule 3. Why n cannot be equal to -1? Look at it and tell me now. It's right here.
You're adding a power. You're adding to the power itself.
Okay. And continue. Let me see if you pick it up. That's not the answer, but continue. So I'll pick it up. Continue.
As n is -1, that means when they add 1 to the power, it would equal to 0. N times the power of 0 is 1.
Hold
And then when you put n plus 1 in the denominator, it will be equal to 0. So it would be definite. Or
it should be what, Nikki? You're correct. You sound like a Mr. Shan student. right up to the point where you kind of went off.
That's what it would be in the
Undefined.
yeah.
It will be undefined. Right. That's fine, honey. That's fine. It will be undefined. Now, hear what she says. If I put -1 right here, so I'm going to have -1 plus 1, which is 0. As 0 cannot exist in the denominator, the function becomes undefined. It can't calculate. Right? So n cannot be equals to -1. Just remember that. Now, all right. All right. Are you all hearing me properly? I see somebody saying that I can speak a little louder. Are you hearing me, guys, clearly?
Yes.
Yes, sir.
Okay, on mine.
All right. You need to turn up your system, Casey. I'm kind of under the weather. I have been not treating my body right. I've been up having classes and marking papers, and I just had to shut down this week. Well, not me. The body says shut down. So I had to obey the body and just got up this morning about 4 o'clock to do some work and turn on the computer and then I said, why am I doing this? I'm gonna go back to sleep and get up 7:30 in preparation for the class. So if you don't hear the excitement in the voice, it's not because of anything else, but it's just maybe fatigue. But this too shall pass. I know you two are going through it because you're working and studying, but it's just one of those things. This too shall pass. All right, let's go. Casey, see if you can turn up the microphone on your device, or you know what I find? If you put in an earpiece, it reduces the distortions so you can hear better. So see if you can put an earpiece in on bunches. All right. All right, let's go. Right. So remember, you cannot have n cannot be equal to -1. N cannot be equal to -1. Okay, sir. So that means if we get a question with n equals -1, we just tell them, say, we can't do it? No. Here goes rule 4. It can be done, but it's going to be done in a very special way. Put it this way. I don't know about Unino, but for me, and it's so like Dwayne, so I can come from country. Dwayne, what kind of country come from? It's sure saying another clock.
No, sir. Straight from Spanish, though.
All right, in the so me a Kingstonian. But guess what happens? Sometimes, you go a country and them give one of the what them call stewed chicken. You can't cook that chicken like you go fry it and eat it, because it have done a gas, it have done a coal. Anybody know what I'm talking about?
Yes, sir.
Hello? Am I here alone?
Yes, sir. I know what you're talking about.
All right, I don't think you guys are hearing me. Let's go again. Are you hearing me?
Yes, sir.
Were you always hearing me?
Yes, sir.
Yes, sir.
Oh, so, all right. I wasn't hearing you because I was fiddling with the microphone on my thing and I turned it to the minus instead of the plus. Stupid me. So, Dwayne, I was asking you come from country, Dwayne?
No, sir. No, sir. Spanish.
All right, cool. Okay, you're tone boy then. Anybody here come from country and know about stewed chicken? We not talk about the chicken you buy and you stew down, Them have a next form and that they layer them and you can't fry them. So the only way you can cook them is by pressuring them. So they meat tough. Right? And a chicken you talk about, you can't even bite them. Who know about that? Who said yes a while ago?
Me, sir.
Yeah, man.
Nikki, you know about it too?
Yes, sir. I'm from Negro, but I don't classify it as country.
Walk off. It's behind Jesus and turn right and then left. That is way, way, way country. Negro nice, man. Negro really nice. Negro nice. Yes, but Nikki and Damian, don't when they cook it nice.
Yes, sir.
Yeah, man. But you can't fry it, If you fry it all, no, me say, don't need gas, your 100-pound cylinder, it don't your bag of coal, you have to pressure it, and it's when you pressure it, and this is the nicest piece of meat. What's the point I'm making? The point is, it is still chicken, but the material says stew chicken, so it has to be prepared a special way. That special way is going to be by pressuring the meat. Okay, sir, they get you. The Spanish man say, I understand that, sir, but sir, what we not understand is how it relate to where you are talking about in number 3. All right, thank you, Dwayne, for asking. Let us look at number 4. The integral of x to the minus 1. But hold on, sir. You just said n cannot be equal to -1. So how you know telling us n is equal to -1? Yeah, man. It's the same way so with the regular chicken. Sorry. And the stew chicken. It is still chicken, but one has to be prepared a special way. The only way one can be prepared, the stew chicken, is by pressuring it because it means tough. The other one, you can do many things. You can boil it, you can fry it, you can curry it, you can fricassee it, you can jerk it, you can you do anything you want to do with it. The one here, when you say anything raised to the -1, the ln function is the only way to twerk it. The ln function is the only way to twerk it. All right? So the integral of x to the -1 or 1 over x, because you know from indices we can convert this to be 1 over x, all right? Because we never normally write it as a negative power, so we can convert this x to the -1 as 1 over x. You will have to include the logarithm of the function. Why, sir, me not lie to you, know. When me leave pre-calculus, me thinks I may leave indices and logarithms behind me, you know. I'm sorry to tell you, no, you haven't. If they're right, yes or no again. Watch me. So the integral of x to the -1 dx. Remember, you know, up here, so the power, you know, up here, so n. And we just tell us that n can be equal to -1. If n is not equal to -1, we're going to use rule 3. If n equals -1, the power up here, so we can't use rule 3, we have to use rule 4. Sir, why we can't use rule 3, sir? Because when you add 1 to the power, when you add 1 to -1, we get 0. And as Aniki said, anything with the power 0 is going to be equal to 1. So the numerator is going to be 1, but the denominator is going to be equal to 0. And we know, say, 0 cannot exist in the denominator. Not yesterday, not today, nor tomorrow, nor even the other days to come. All right? So we have to use ln. So once this is something with a negative first power, if it's a negative second power, you know, you're fine. If it's a negative third power, you're fine. The only power that it have to work like this with the ln is when it is -1. No other power, just the -1. And of course, my constant of integration, because I'm talking about an indefinite integral. Now, here, x has to be greater than 0. And this is something that we've learned, in pre-calculus. Look, the condition x greater than 0 is added because only positive numbers have logarithms. You cannot take the logarithm of a negative number. You can't take the logarithm of a negative number. So because that is the case, we are going to be using the absolute value. We're going to be using the absolute value of x. So when we write it, we're going to write the absolute value of x. See here, so? So writing it from here, so, to here, so, to write ln, the absolute value of x. All right. So here goes a teacher at the moment. What is the absolute value of x, sir? The absolute value of x is always a positive number. So the absolute value of 2 is 2. The absolute value of -2 is 2. The absolute value of -5 is 5. The absolute value of -6 is 6. So what is the absolute value of 6 then? Still 6. So the absolute value of a number is always positive. So when you take the absolute value of a positive number, it is still that positive number. But when you take the absolute value of a negative number, it becomes the inverse of it, which is the opposite to that number. So the absolute value of negative 100 is going to be positive 100. Negative million, positive million. You get me? Hello, somebody. Remember, you have to talk to me in class, so I can know you're following me.
Follow
Yes,
it,
sir.
follow.
All right, good job, you man. Just keep me awake, please. Especially I'm under the weather. I need company today more than ever. All right. So I'm just going through the rules. I think if I go through the rules and you understand what the rules are saying, and I give you examples, when we start the question, these rules will just come into play, and then you don't even have to study this. You can just reel them off. All right. And of course, x cannot be equal to 0 because you can find the log of 0 and tell what you get. Alrighty, rule number 5. The integral of a natural exponential function is the exponential function itself. G's on P's. I am teaching a calculus 2 class, and it's one of the things that I have to keep reminding the students. The integral of the exponential function is the exponential function itself. The only difference is you're going to differentiate the function and then reciprocate. You're going to differentiate the function and then reciprocate. Talk to me. The integral of e to the kx dx. You notice, you see that e to the kx? Can you see the e to the kx here again? Yes, no, maybe so?
Yes, sir.
Good. So the integral of e to the kx is e to the kx. So the integral of any exponential function, write back the exponential function. Is the exponential function ugly? Write ugly. Is the exponential function pretty? Write pretty. Is the exponential function in between? Write in between. Anything them give to the exponential function, write it back. But the only difference now is that the function atop the e, this kx that is in my highlight in blue, you're going to differentiate it. And when we differentiate kx, we're going to get k. And then we reciprocate the k. We get 1 over k. That's all that there is to it. Let me say that slowly. Whenever you are integrating the exponential function, and keep students, I don't expect any of this to come on your section B, but I expect questions like this to come under on your multiple choice. It may come on the essay paper, don't get me wrong. But more time I'm seeing questions like this on the, when I'm teaching like AdMath, I'm seeing questions like this coming on the MCQ as opposed to the ETQ. Business calculus. Expect this on your section 2. Expect this on your section 2. Right? That's also for the MCQ, right? But wherever they give you, you should be in a position to do it. Let me say it again. The integral of an exponential function is the exponential function itself, and then you're going to differentiate the function and then reciprocate. You're going to differentiate the function, then reciprocate. Sorry about that, yeah? Let's go. When you're integrating an exponential function, the result is going to be the exponential function itself. Then you are going to differentiate the function atop the e. Whatever answer you get, you're going to reciprocate it. You're going to reciprocate it. Put 1 over it. All right? That's what we're doing. And of course, I must have my plus c, which is my constant of integration. Very important. Very, 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 very important. Right? So the integral of an exponential function is the exponential function itself. And then I'm going to differentiate the function, reciprocate it, plus c, that's my final answer. All right. We soon come to some examples, and I just want to go through the rules. It says the integral of a constant times a function equals to the constant times the integral of the function. So what I'm saying to you is that if I have a function here, and remember this is known as an elongated s. I want s, but we just stretch it. All right. So when I'm integrating kf, k is my constant, so I can take out the k. See that so? I take out the k and then just integrate the function f of x. So that's what this means. The integral of a constant k times a function f is going to be equal to the constant, see that so? The constant out here so times the antiderivative, which is the integral of the function. You see that?
Yes, sir.
Yeah, man. Good. Remember, I needed to talk to me to keep me awake. All right. Of all the Saturday mornings, this is the Saturday morning when I feel like I want to go back to sleep. All right. So it says the integral of the sum or difference of two or more functions equals to the sum or difference of their integrals. So I'm going to understand that. Not a problem. Let's go. So you're integrating f of x plus or minus g of x. Watch what it is to be. It is going to be the integral of f of x dx. Then you put the plus or minus in between. Then you find the integral of g of x dx. So it says the integral of the sum or difference. Sum or difference of two or more functions is going to be equal to the sum or difference of their integrals. So it means like in the chain rule for the differentiation, when you integrate, when you differentiate individual terms, are the same thing we're talking about with the integration. And I have some beautiful examples here to show you. It's the same thing for the integration. So if I get something with this plus this or this minus this and so forth, I'm integrating individual terms. That's what this one is saying at rule number 7. All right. Rule number 8 says the integral of a negative of a function equals a negative of the integral of the function. Same thing like the one up here. So, all right, because the negative sign is going to be treated as a constant, just like my k up here. Just like my k up here. So the negative of a function, I'm going to take out the negative and just integrate the function. When I finish, I just multiply by this negative sign by the function, just like this. When I finish integrating this thing, I just multiply by a constant to my answer. Good to go. All right. So let us look at this here example. Remember, today is going to be a rough-ish class because we're going to do a lot of stuff. Now, these examples are new to both groups, CAPE and business calculus. So I'm just going to ask that you just work with me. I know some of you may still be in bed lying down and just listen to what I'm saying. But if that is the case and that's how you feel comfortable and that's how you learn, I'm going to ask you to just grab a paper, grab a book, grab a pencil or a pen, and let's go, please. I'm finishing this topic today, finishing it today, right? Even at the expense of not doing anything else, I cannot come back to integration next week. I have 2 weeks left, and I have 2 topics left. 3 topics. No, 2 topics, because we ended up with integration in this, right? 2 topics left, and I have 2 weeks left. So I know I can finish the syllabus today. I'm not worried about that. But I wouldn't mind if I'm able to finish the syllabus next week. So the following Saturday, we can just run past papers. We meet, and from morning, we just run past papers. All right, let's go. So we're integrating 1 over x squared dx. 1 over x squared dx. Now, again, I did say to you earlier that your indices will come into play here. Your indices will come into play here because I'm converting, I'm rearranging to give me the integral of x to the minus 2 dx. Everybody, so I get x to the minus 2?
Yes, sir.
Very nice. So we'll get our x to the minus 2. Now remember, the rule says add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Hold on 1 minute, please. Let me just it's just All right. So we're adding 1 to the power and dividing by the new power. Always remember that. So look, I'm adding 1 to this negative 2. See it here, so this plus 1. And then going to divide by the new power. See here, 2 minus 2 plus 1 is down here, so minus 2 plus 1. Then I'm going to have my plus c. Always have your constants of integration when you're doing an indefinite integral. An indefinite integral is one where you don't have a power, and an upper limit and a lower limit. All right. Simplifying gives. Remember now that c is a constant of integration. Negative 2 plus 1 is going to be negative 1. And negative 2 plus 1 is still negative 1. And then this negative 1 here can just be negative 1 x to the negative 1 here. But because we don't normally write our answer as a negative power, what we can do is just to flip this back and put this as negative 1 over x to the positive 1. And this will be our final answer.
Sir. Question: If the x to the negative 1 was divided by negative 2, you'd have negative 2x raised to negative 1.
All right. So problem. So whenever I get the integration question, it's like how in differentiation we have the quotient rule. Denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator, all of the denominator squares. We're not adding the rule in integration. We have enough integration rules, create some things. Plenty enough rules for integration. Too much if you ask me. But for the simplicity of your syllabuses, we are limiting them to just a few. All right. So whenever you get something like this, a fraction, see if you can rewrite a fraction before you do the integration every time. Every single time. If you can't rewrite the fraction, there's going to be a substitution method to it. We have to substitute. We have to substitute in order to get some stuff. All right, so let's go. So you have the integral of 1 over x to the second power dx. Remember that dx is telling me what it is that I'm differentiating with respect to. So I can't give you the integral of 1 over x squared dr or dp or dq or ds or dy, because it means that I have to be integrating with respect to x. That now will become a multivariable function. And that's one other thing that we're going to get into shortly. All right. So when I differentiate 1 over x squared, rubbishness. When I integrate 1 over x squared, remember what it is that I'm doing. I'm going to try and rearrange my function first. How do I rearrange my function? My function is going to be written in the index form. The index form. How do I write it in the index form? I'm going to have x raised to the negative second power. Sir, how did you get that? Remember 1 over a to the m is equal to a to the negative m. 1 over a to the positive m is equal to a to the negative m. Always remember that. Indices, we did that from long time. Matter of fact, while I was teaching my CAPE students that you business calculus students were doing pre-calculus at the time, first semester. So you both learned it at the same time. All right. And then now that I have it in a form that is not a function, a rational function, I'm going to have it as x to the negative 2. I'm adding 1 to the power. I'm dividing by the new power. I'm adding 1 to the power. I'm dividing by the new power. So x to the negative 2 now becomes x raised to the negative 2 plus 1, because I'm adding 1 to the power. And then now I need to divide by the new power, negative 2 plus 1. And then I have my constant of integration, I plus c. Remember, I add 1 to the power and divide by the new power. Now I'm simplifying. Negative 2 plus 1 is negative 1. So -1 goes here, -1 goes here, plus c. The same thing as this -1 is the same thing as just a negative x to the -1 plus c. But we never normally write our answer as a negative index. So I can reconvert it now, just like I did it right here, as 1 over x to the +1, or the simply 1 over x plus c. And that will be my final answer. Is it clear?
Yes, sir.
All right. I'm going to ask you to take a minute and just work through this in your head space. You don't have to understand it fully. I'm just going to ask you for a minute. Just 1 minute I'm going to give to you. To just look at it, and then I'm going to go through. I just want to point out some stuff. And then we'll take it from here. All right. All right. So let's go. Here's a question. 3x cubed minus 2x to the 4th plus 7x minus 2. And the answer is integrate it. From rule 7, let me show you what rule 7 is. And when you're doing the question, you don't have to write rule 7 and rule 6 and rule 5 and rule 4. No. I'm just pointing out to you to show you that I'm actually applying the rules. The integral of a sum or difference of two members of a function is equal to the sum or difference of their integrals. Remember, when you get the functions added or subtracted together, You can just break it up and integrate them individually. That's what we're doing here now. So we integrate this piece first with respect to x, then integrate this piece next with respect to x, then integrate this piece next with respect to x, and then integrate the last piece with respect to x. All right. So we're doing 1, 2, 3, 4 different integrals. 1, 2, 3, 4. All right. So we're integrating them individually. Now watch me. Rule number 8 has a negative sign. I said that the integral of a negative of a function is equal to the negative of the integral of the function. Means which is a factor of the negative sign. Similar to rule number 6, where I have a constant. I'm just factor it out. All right. See, this all right enough, so I'm write it back. The one you know have the negative sign, it's a can factor it out. So now back it out. See here? And back it out, so I'm going to have 2x to the 4th, right here, so left. The one here, all right, so I'm going to just write it back. The one you know is also a negative sign. So I'm backing out the negative sign and just give a 2. But what on this one, sir? This not look like the function I said when you integrate in 1, you don't really write 1 dx, you just write dx. All right, I will come back to that. So the other rule number 6, you know, as I pointed out here with the constant, is that when I have a constant, I can back out the constant. Watch it. The 3 here, so I back it out because it's a constant. The 2, I back it out is a constant. The 7, back out. The one a constant, you know, back it out. So now we write 1 dx. That is when we write dx. And that's rule number 2. All right. Remember now, sir, do I have to do all of this in the question? No, I'm only showing you now what to do. You will find out how easy the topic is. We can just go ahead and just write your answer in 1 line. All right, I'm only showing you this so that I can get you to the point where you can integrate on your own. All right. Let's go. Recall, we're adding 1 to the power and then divide by the new power. We're adding 1 to the power and then we divide by the new power. The 3 here, so, and the 3 directly, so. We'll add 1 to the power, x to the 4th divided by 4, see right here, so. The negative 2 right here, so. Write it back right here, so. Add 1 to the power, x to the 5th over 5, see right here, so. Plus 7, right here, so. Add 1 to the power, which is at 1 already. So now add 1 to the power and get 2. Add 1 to the power and get 2 divided by the new power, 2. So this becomes x squared over 2. See right here, so. This one is x to the 0. So you add 1 to the power, it becomes x. See right here, so it's just 22 times x, and I have to put my plus c. I have to put my plus my constant of integration. Are you hearing me? Are you with me? Are you understanding?
Yes, sir.
Is there anyone in class that don't understand? Hello? Is there anyone in the class that don't understand?
Sir, I don't understand, sir. What
What
divide
not,
chip in and chip out, sir?
what you not understanding? Talk to me. Tell me what you not see.
Sir, from the beginning of this question.
Alright. Don't worry about it. You will see another question that I can go through. Don't worry about it. Just try and catch up on this last piece here. So what I'm doing now is just simplifying. Integration here finishing it. So once I remove the integration sign, or once I have integrated, I'm removing the sign. So once I start adding 1 to the power and dividing by the new power, I'm not writing about my elongated s because it would have suggested that I've already integrated it. All right. All right, let's go. So 3 times x to the 4th over 3 is 3x to the 4th over 3 times x to the 4th over 4 is 3x to the 4th divided by 4. See, correct yourself? Negative 2 times x to the 5th over 5 is negative 2x to the 5th over 5. See, correct yourself? 7 times x squared over 2 is 7x squared divided by 2. See, correct yourself? And this negative 2x is right here, so let's see right here. Question done. Sir, is there any way I could move from I could move directly from here, sir? Cut out the whole other piece here and just jump to here, sir? Absolutely there is. I'm only showing you, since I gave you rules, I'm only showing you how the rules apply. I want you to understand that you are actually using rules. But watch me. Remember I said to you now, the third one I gave you, add 1 to the power by the new power, is going to be the most used of the rules. Watch me, don't blink. Okay, see, this is your opportunity to see this again. 3x to the third, add 1 to the power divided by the new power. 3x to the 4th over 4. 3x to the 4th over 4. Go back up here. Remember, you're adding 1 to the power and dividing by the new power. Negative 2x to the 5th over 5. See here? Negative 2x to the 5th over 5. Work with me. 7x to the first. 7x to the second over 2. 7x to the second over 2. Work with me again. Negative 2, certain number x. Let me add an x to it. Yes. 2x. Negative 2x plus my c. Tell me that you see it.
Yes, sir. Yes, sir.
Tessie, you see it?
Yes, sir.
Good job. All right. Because it is some of the color coding right here, so let me just project it and hold on there. Whoa. Boy, I have a eucalyptus mint. Just trying to help to clear my stuffiness for class. And trust me, that I saw that a potent piece of eucalyptus a while ago. It's strong. I can breathe clearly now. Let's go. Let's go. Let's go. So I have the same concept here that I had before. Remember, we can do the question and move directly from here to here. But I'm showing you how it is. I want you to have that understanding of what it is that we're doing. After this example, I don't think I did anything else. Right? You notice after that example, I just do a 1 line or at most a 2 lines. All right? This is just my introductory lines. I want you to see how the rules take effect. Last example on this one, before we do it the grown-up way. So I have 1, 2, 3, 4, 5 terms. So it means that I'm going to integrate it 5 different times in pieces. Not integrating the function 5 times, but in pieces. For x to the 5th is integrated by itself. I try to color code them. The first one here. The 7x cubed. 7 is here. The one here is this. The one here is this. And the one here is this. And I get them for the rule number 7. Rule number 8 and 2. I can break it out. 4 is a constant, so I can take it out and put that here. So 7 is a constant, I can take it out and leave the rest. The negative 6 is a constant, I can take it out and leave the rest. I want to stay as it is. The negative 9 is a constant, I can take it out and do the stuff. Remember, we're adding 1 to the power and dividing by the new power. Every single time we add 1 to the power divided by the new power. Every single time. When we are integrating, we always add 1 to the power and divide by the new power. Every single time. This is 4, and this now becomes x to the 5th. It now becomes x to the 6 over 6. That's plus c, because I'm integrating an indefinite integral right here. So then I have my plus c. That's 7 is this. And it's x to the 3rd. So I'm adding 1 to the power. It becomes x to the 4th over 4 right here. So plus c. The minus 6 is right here. This is x squared. It becomes x to the 3rd power over 3 plus c. The one here is x to the 1st. Add 1 to the power, becomes x squared over 2 plus c. Right here. This is minus 9. And integrating dx, I'm going to get x. This is 9x plus c. Now, and then I'm going to have my plus c as my overall constant. Watch me. Is it a little c here, sir? Plus a little c right here, sir? Plus the 1 here, sir? Plus the 1 right here, sir? Plus the 1 here, sir? I will equal to the big C. So I'm going to understand that, sir, because based on the mathematics, we're not always a teacher from a long time. That was like 5C to me. May I agree with you? But work with me. Work with me. When you go to the supermarket, you see, and you buy your item 1-1, you really not see how much GCT you have spent. So let's just do a comparative test. Sorry, let's just do a comparative test. Dwayne and Dan went to the supermarket. Dwayne mean, you know, want to spend the money, you know. Dan, you know, she said, money can't eat. And one time I come to the supermarket, you look to me now come to 5 times, and one time I go. Dan buys 5 items, and she spends $300 on tax for the 5 items. $300 on tax. The Wayne, on the other hand, now decides that he might go to supermarket 5 times. The first time he spend, he pay $100. The next time he pay, he spend $100. So he spend $200 per tax. The next time he go, he spend $25 on tax. Then he spend $50 per tax. Then he spend $25 per tax. That 100 plus 100 is 200. That 200 plus 25 is 225. That 225 plus 50 is 275. And that 275 plus 25 again is going to be $300. So they both spend the same amount of money on tax. The only difference is Diana did everything one time. But in this side, say, the tax money look too much, so in this side, say, I'm going to take it out. Case in point, they're going to tell me a story and don't repeat it because it's very close to my heart. I remember years ago, before some of them were born, years ago, I was teaching right at the college. And, you know, when you just start work, the government will take my tax out time money for about 3 months. Yeah, man, I feel good. I feel good, man. September, I get my full pay. Your tax not draw out. He said, what? Yes, so nice. October, come and get my full pay. My tax not draw out. And he said, what? Yes, so nice. November come, full pay. Right? And the sad thing about it is that nobody was there to explain to me what wrong. So now December come, and me don't tell God, say, I'm gonna buy this, I'm gonna buy that, I'm gonna buy whatsoever this for my Christmas. Me get my little envelope in my little check now, and me decide, say, I'm gonna jump on my mom, so go down and town to change the check, because you get a little 1 hour break. Jump on the 83. Go at town, open the envelope, put on the something, and me see enough money come off on the fee. Boy, they said, I don't know where the eye water come from, but it spring up quick and fast. I turn up in the bank and the eye water drop out of my eye. All of those plans that I had known to do for Christmas got shattered because of money cut. I'm going to change the money. I'm going to go back to school and I'm go and I say, hey, I want to make a mistake. I said, no, sir, I'm lucky. Actually, you just get little work. My first job. That's why this happened. So the government pay rough. What's the point? When you look on the paycheck, and I'm speaking specifically now about the business calculus students, and you see how much money they take out the income tax alone, that is somebody else's full-time salary for the month. Talk through. Allow me to tell. Wait, only the business calculus students, allow me to tell.
It depends on your salary, sir.
What depends on the salary?
How much the income tax? I don't think I reached that level yet.
All right. Sorry, I'm just reading the message. All right. Sorry, say that. You said it again? Depending on your salary, the income tax, what? Say it again.
No, because they're drawing comparison to the income tax and maybe it being equal to someone's salary for the month.
Mm-hmm.
I'm not at that level as yet.
No, man, you will get to that level soon, man. No, man, but it's true. It is heavy stuff. Heavy stuff, man, because you know, and I know they don't take income tax if you're working, you know, below a particular threshold. But once it is that you start working above the particular threshold, then start taxing you. What's the point I'm making? The point is, when you look at your salary, the income tax is taken out, and you're monthly paid. You're monthly paid. The income tax is taken out one shot at the end of the month. It seems like enough money. But if you are weekly paid, The income tax still come out, but it's a smaller amount of tax that comes out at that point in time. But if you add up the tax that comes out every week, you'll recognize it's the same tax that will come out for the same month. What's the point? Then look see here, then look see here. When I add it up, it will give me the same big C. So I don't need to write 5C. I just write 1C. All right? And then I do the same stuff like I did before. 4 times x to the 6 is 4x to the 6 over 6. So 4 times so on. And when I simplify all of here, 2 can go into 4 to give me 2. And 2 into 6 gives me 3. And 3 can go into 6 exactly as 2 times. So I just simplify that here. Follow me? But I can jump from here directly to here. Let's go. For this one, I'm going to do in 2 steps. 4x to the 6th power over 6. See here, so 4x to the 6th power over 6. Plus 7x to the 4th power over 4. See right here, so minus 6x to the 3rd power over 3. See right here, so x to the 2nd power over 2. See right here, so minus 9x. See right here, so plus the c. And why I say 2 lines is because now I recognize that this can be simplified. So is this one. So once I can simplify them, simplify them. Once it can be simplified, simplify it. All right, and that's it. All right, here goes a true test. Try that one for me, please.
Number 4, sir.
Number 4, yes, sir. Okay, press pause, please. I'm sorry to disturb your work here. Press pause. I'm feeling led to speak on a matter. So I'm having a private conversation with a student now. I'm going to identify the student, but I'm just going to talk about a particular issue. So as I said, for those of you who just joined, I am under the weather. I just have the sniffles. I mean, I don't have a chest cold. It's just mainly nasal, and it starts off with a sore throat. I don't have a sore throat anymore, but I'm just very nasal. And when I say nasal, I mean stuffy nose. So, I do a lot of eucalyptus, like I'm having a eucalyptus meat now, just to clear the nasal passage. So I'm very nasal, but I'm also very tired because, I have integrated the GAPE students with your class because some of what you do, they are doing. Time is against them more than you, because they should have done their exam from Monday of this week. Thankfully, CXC extended the time. So I invited them. They started this topic before, but I said to them, come, so they can get a little refresher. So this is like a revision class for them, so to speak. But I also recognize, not just with business calculus, but with both groups, that there's a lot on the table. There's a lot on the table. You have mid-semester exams, you have coursework pieces, and everything feels like it's just coming down on you all at once. I don't want anybody to break at this point in time. This is not the time for you to break. This is the time for you to strategize. Like I had to do that the other day. And when I said the other day, I had to do that this week. 2 days ago, I got up, say, yes, I'm ready to work. And the body says, no, you are not. Go on, believe the man sleep. And I don't want to sleep for maybe after 2 or 3 hours. And I can survive. It's one body, you know. And if you don't take care of it, it's gonna take you out. Strategize. You can only do one at a time. So what I would say to you is, I am going to be doing business calculus today. You commit that I'm going to spend an hour or 2 hours on business calculus. You spend the 2 hours and complete your business calculus. And then you do the same for the other areas. This is not the time for any of you to feel flustered. You know why? It's too close to exam. And you're going to go into the exam feeling flustered, and your true potential will not come out. Pace yourselves. Every one of you. Every single one within the class. Cape students, I know you may have on the 24th when you have your first exam, which is integrated math, my exam, in the afternoon, those who are doing physics unit 1 will have physics in the morning. So you will have 2 exams on a day. It will run just like that. So pace yourselves from now. Calm down. Just relax yourself. Don't get flustered. It's a plan of the enemy to throw you off. And I promise you that you'll be fine. Trust me on that. You're speaking to somebody who has been there. I will if I want to ball. Plenty enough. I'll win at the exam and ball. How about them asking for do? I'm a ball and say, sure, you can't bother. And then I hear a voice say, can't bother. Oh yes, it's the 23rd. Yes, it's the business calculus that, sorry, it's the Cape students that begin on the 24th. Not the Cape, sorry, the CCCJ students begin on the 24th. Because it's a public holiday for us in Jamaica, but CXC don't recognize regional holidays, so yes, we're going to have your exams on the 23rd. So I'm saying to you, it's a part. If you're not feeling pressured, it means that you're not doing any work. So the mere fact that you're feeling pressured, it means that you're working. All right? Pace yourself. So what I want you to do, finally, what I want you to do, you're now in business calculus class. Forget about the other pieces of assignments that you have outstanding, and let's just tunnel vision with the business calculus so you can fully get what sir is talking about. When we're done class and don't teach this, then you can go take it up. But if you're thinking about everything else, if you miss this, and then you're not going to learn it, and then you have to go relearn it. So forget about everything else. Tunnel vision. And then we can talk about the others after class. All right?
Sorry, I want profit, man.
Divine intervention.
As we have 2 to submit today.
Don't worry about it, man. You just focus on the business calculus now so that you don't miss this, so you don't have to come back to this topic. Because I remember certain man done that topic today, you know, so you don't have to come back to this. And you should be fine. I promise you, you'll be fine. I have been there many times over, and I survived. You too can survive. All right, continue working, please.
Sir, finish.
Good job. I give the others a few more minutes. All right, considering that I have to go, I'm going to project my answer and tell me if you agree with me.
Yes.
Yes, sir. Yes, sir.
All right, yes, Abraham.
Yes, sir. I got that too.
Great. All right, so let us move it quick and fast now. Number 5. So number 5 right there, quick and fast. So what I'm about to do with it now is just to do some quick and fast calculations before I move into some other things. So as soon as you finish, just let me know.
Finish, sir.
Excellent job. Come guys, hurry up. The rest of you I need to hear from you also.
Yes, sir. Finish.
Talk to me before you stay. Agree with it?
Mhm.
Yes, sir.
Did you all have your plus
Sir.
C's?
Yes, sir.
Good job. Love the sound of it. Cassie and the rest of you, Mealy,
Sir.
Shakila. Yes, honey.
Sir, that's what I got.
Very nice, very nice, very nice. I want to work with me. Not, I don't want anybody to sit down and not do anything. Oh, see another one there. Quick and fast, quick and fast, quick and fast. As you say yes to me, I'll move on to the others.
Finish, sir.
That's what you got to Tania.
Yes, sir.
Good job. The rest of you, come check to see if you don't get it. When I hear the yes, I'm putting the
Yes,
answer.
sir. That's what I got.
Good. If you don't get it, stop me. Because I want to make sure that you get it. Come, I want all of you to do work. Come, see number 7 there, start.
Yes, sir.
Finish, sir. Yes, sir. Got that.
Very nice. I'm hearing you. Very nice. Move on to number 8. Guys, quickly, quickly, quickly. Damien, I need to hear from you. Dan, I need to hear from you. Come on, come on. Quickly, quickly.
Finish, sir.
Yes, sir.
So you can go back up on number 6, please.
Finish, sir.
Finish, sir.
All right, Cassie, can I move from number 6 now?
Yes, sir.
From last time, I tell you, anytime I ask me to go back, tell me when you finish. There are others who are waiting. Where was I? Number 9 or number 8?
9.
Tell me when you finish when I ask me to go back, please. Are you okay with number 9 for the answer?
Yes, sir.
All right,
Yes, sir.
let me give you that last one to do, and then I'll do a little assessment. Start on that one, please. Then you finish that one, we'll talk.
Finish, sir.
All right. Got that answer?
Yes, sir.
All right, good. Now, this is my general question. How are we? Diana?
I'm okay, sir.
Very nice, very nice. Damian, Shaquille.
Sir, where you get the 9x squared?
Following, sir.
Add 1 to the power divided by the new power. Yeah, add 1 to the power divided by the new power.
Sir?
I'm coming to your case. I mean, answer me now, answer me, and you don't say nothing more to me. I don't know if you have answered this question.
Yes, sir.
Yeah, man. So, thank you, then, Mr. Man.
Thanks.
Yes, you're welcome, honey. Cassie, go ahead now.
So you can show me number 8 question, please.
You're coming to you. All right. Now, I want you to be fully honest with me. While Cassie looks at number 8, I want the rest of you to be fully honest with me about your level of
Yes, sir, I'm finished.
great, about your level of understanding, including you, Cassie. Say from a scale of 1 to 10, is there anybody in the class that is at a 5? Okay, answering silently. Is there anybody that is at a 7? Thanks also for answering. So am I to assume that everybody's between an 8 and a 10?
Yes, sir.
Yes,
All right,
sir.
cool. It's really not difficult.
Yes.
Yes, honey.
So what did
Go
you
ahead.
say, sir?
I'm just saying that means everybody's between an 8 and a 10. That means that you're understanding the topic. Are you understanding, Kes?
Yes, sir.
Good job, honey. All right. Now, as I said to you, it's not. It's when it's something hard, you tell us it's hard. We're not lying to you. We're not lying to you one week. If it's hard, I'm gonna say it can come. That when you're rough enough, but come. Right? All right. So I have a few more, but I don't want to give you those yet. Right? I'm just going to jump to number 15. I will give you the documents so you can have those additional ones to do for the stuff. I found it very fun to just sit down and write these questions and sit down and do the solution itself. So let me just tell you what some of my very loving but unnice students did to me last night. So I'm there doing the solution and writing the questions and doing the solution. I made a grave error in my calculation. And one of my students finished me in class. Then, sir, me want to know how you add up this and this and get 21. That don't make no sense. And after me done laugh after myself and auntie said the matter closed. My home student said, but by the way, sir, if you look, me say you're still on it. Point I'm making is I can make mistakes. I can make mistakes, but I really find it fun to do the questions, to write questions for you. That I generally write out of my head and then sit down and do the solutions for you. Your responsibility, just like last night. And I don't correct that document yet, so I have to go correct it, not that I remember. Your responsibility is to check to see if it's the same answer that I did. And if you don't, you say, sir, check your answer again, please. Because I know I'm right. And that's why I teach you. So I am not offended by that. In no way, shape, or form. As I said before, I'm the first to laugh. I laugh at myself and say that. Then doof, how you can add them something and reach 21? It don't even reach 10, let alone 21, right? But it's one of those things. It's life. And when I give you the questions, the point is when I give you the questions, work them. You don't get what I get, sir. Check that one day. Sir, I'm convinced you are wrong because I learned the topic and I say it. But that's the level of independence that I want of my students. So I'm going to ask that you just work on those what it is that sir is asking of you. Very nice though. All right, let us look at number 15. Number 15 is slightly different. 11 through 14 has the same general feel to it. But number 15 is slightly different. Now remember I said to you that and I'm only going to give you the first piece and ask you to do the rest of it on your own. Remember I said to you that we change position. I don't know why I'm feeling sleepy. All right. We don't have like a quotient rule, so to speak, for the integration. So whenever we get a question looking like this, we have to go and do some rearranging. So rearranging the question makes it easier for us to work. Now, if you look at it, x to the 9th minus 7x to the 7th plus 2x to the 5th minus x cubed plus x squared all over x squared dx. And we need to go ahead and integrate. Yo, watch me. We don't have a quotient rule. So you know what you're going to do? Is each term in that denominator, rubbishness. Each term in the numerator is being affected by the denominator x squared. So really and truly what I have is x to the 9 over x squared minus 7x to the 7th over x squared plus 2x to the 5th over x squared minus x cubed over x squared plus x squared over x squared. That's what I have. So you're going to divide each term by the denominator, and when you do that, you're going to simplify it. So it says each term in the numerator, as I just told you, is affected by the x squared in the denominator. You need to perform the cancellations first and then do the integration. So look at what is supposed to happen. X to the 9th over x squared is going to be x to the 7th. See if I get so? 7x to the 7th over x to the 6th is 7x to the 5th. See it right here, sir? Remember the indices says when you're dividing and the powers are the same, and the bases are the same, you subtract the powers. So 9 minus 2 is 7, right there, sir. 7 minus 2 is 5, right there, sir. 5 minus 2 is 3, right there, sir. 3 minus 2 is 1, right there, sir. X squared over x squared is 1. And then you would have simplified your question from up here, sir, to here, sir. Talk truth. That one look more attractive than the one up here, so don't.
Yes, sir.
Yeah, man. Go ahead
Yes,
and
sir.
go ahead and integrate this for me now. So this is what you need to do when you get a question like that. Start that for me, please.
Finish, sir.
Finish, sir.
Good job. What about the rest of you? Come on, what about the rest?
Yes, sir. Finish.
Next. Let me know if you got that.
Yes, sir.
Yes, sir.
Yes, sir.
All right. Okay. All right. Okay. So let us look at some indefinite integrals. That is when you include the natural logarithm. As I said before, we're going through this. It's now 10 o'clock. 2 hours in, and we are moving. Let us see how best we can look at some of these other stuff. So we're looking at some indefinite integrals, including that will include the natural logarithm, the ln function, right? So if I give you something like this, the integral of 3 over x, 3x plus 1 dx. When you look at it, you'll recognize that, but sir, hold on there. Not like the question you just gave us, where you can divide each term by something and simplify. That one I can't simplify anything further, sir. Because it's not that you have the 3x plus 1 in the numerator and the 3 in the denominator. If that were the case, sir, we could have integrated that easy. But now you have it the other way around. Sir, we can't do this question. No, man. What I'm going to do, I'm going to factor the whole number. The whole number. 3 and put outside. Remember the rule? It says once you see a rational function with a constant in the numerator, factor the constant once it's greater than 1. And then you'll have the function in the form 1 over x. Then we have the function in the form 1 over x, where x is a function, as in the example above, 3x plus 1. So once you're given once you're given a rational function with a constant, it has to be a constant though. A constant is a number that stands alone, a whole number. Or it could be a fraction too, but it don't have no variable beside it. All right? And it's greater than 1. You're going to factor it out. It's going to factor it out, then you're going to have the function remaining in the form 1 over x. right? X is going to be the function. As in the example above, it's going to be 3x plus 1. Now, so I'll have 1 over 3x plus 1. Using the rules of indices again, I can say this is going to be 3x plus 1 raised to the negative first power. Using indices, because remember the 3x plus 1 is together, it's married. I can't separate it as a 3x plus 1. It is 3x plus 1 as one single term in the denominator. Right? Now, look at what is going to happen. So I'm saying 3 times the integral of 3x plus 1 to the negative first power. Remember, from the rule above, Sir did say that when the power is -1, we must only use the ln function. Anybody remembers that? When x is raised to the negative first power, when we do this stuff, it must be ln, the absolute value of x. Everybody remember this now?
Yes, sir.
Right? So x to the negative first power, we have ln, the function, plus c. Watch this. This 3 is this 3 out here now. Then we have ln, see the ln here, the function 3x plus 1 plus c. Then sir, where the 1/3 that come from? Thanks for asking. We are going to differentiate the inside here and then reciprocate the differential. Oh, the differential of 3x is 3. And when you reciprocate 3, you're going to get 1 over 3. See to your third? Yeah. But, sir, you never differentiate this. You remember, so the differential of a constant is equal to 0. So that one that goes automatically. Oh, so I have this, sir. That means I've factored out the 3. And then now we have 3x plus 1 to the -1 to integrate. Correct, sir? Yeah, man. And when you integrate this now, what you get? All right, sir. You're going to get, because it's -1, sir, you're going to get the ln function. So you're going to write ln, then the 3x plus 1, absolute value, sir, plus c. Yeah, but that is incomplete. Also, sir? Oh, sir, you remember you have to differentiate the inside of the parentheses too, sir, and then you reciprocate it. Very good. Now differentiate the inside of the parentheses. All right, sir. The differential of a constant is equal to 0. So when I differentiate positive 1, I get 0. Very good. Continue. And when I differentiate 3x, sir, I'm going to get 3. So the answer is 3, sir? No. Remember, we need to reciprocate. Yes, I forgot, sir. So when you reciprocate it, sir, you're going to get 1 over 3. Very good. And then this is what I get right here. Everybody understand that?
Yes, sir.
Good. And then now, when you multiply 3 by 1 over 3, you get 1. So you have just ln, the absolute value of 3x plus 1 plus c. So this is the integration of this piece of here. Take a minute, look at it, and right here, let us have a conversation so we can move on. Are we good now? Woohoo.
Yes, sir.
All right. All right, so note, so we differentiate what is in the absolute value and then we reciprocate it. All right. Now, let me just prove something to you here. Then, sir, when we do the question, we have to prove it. No, man. For teaching purposes, I just want to prove to you. So I'm getting this to be my answer. So to prove to you that the opposite of differentiation is integration and vice versa, I'm going to now differentiate this function. So I'm going to let y be equal to the answer. And then I'm going to differentiate it. The differential of ln x is 1 over x. You know this because we've done differentiation before. The differentiation of ln x is 1 over x. This is ln, and all of this represents x. So the differential of ln x is 1 over x. The differential of ln x is 1 over x. So it's 1 over all of that. See here, 1 over 3x plus 1. Bam. And then now we need to differentiate what is inside of the absolute value, which is 3x plus 1. And when we differentiate 3x plus 1, we can get 3. And 3 times 1 is 3 over x plus 1. So it's 3 over x plus 1. See here? 3 over 3x plus 1. 3 over 3x plus 1. So we know that our answer is correct. All right, watch me now. So the questions will not always come and look like this. 3 over x, 3x plus 1, but at least you'll know what will happen. Come on, don't do that. I have another question here for you. It involves the natural logarithm. Just remember, a hint, whenever something is being raised to the negative first power, be careful. If something is being raised to the negative first power, be careful. Like that one down here, so negative x to the negative 1, be careful. On the mark, get it both, start for me, please. Every Jack man and woman, start for me, please. Finish?
Yes, sir.
You can't tell me to get that. I know all of you will get the 4x squared plus 5x, but did you get the negative ln absolute value of x?
Yes, sir.
Very nice. Miss Cal, what say you?
Yes, sir.
Good job. Troublesome. Wow. Sir Sean. Let me give you a hint. When you have the square root of x, what does it work out to be?
X raised to the half.
Very good. Woohoo! X raised to the half of business gal. That is from indices and logarithms, you know. That is from indices and logarithms. That is not something that Mr. Shan will teach you. That is, if you did pre-calculus with me, yeah. But coming to the business calculus class, you should know that the square root of x is x raised to the half power. The cube root of x is x raised to the 1/3 power. So one of the things that I would have given my CAPE students for indices is the nth root of a is a raised to the 1/n. All right? So that is a hint. The square root of x is x raised to the half power. Very nice. Start for me, please. Obviously. Hello? Obviously.
Finished.
Tell me if that's what you got for your answer. Yes, we can move on. No, we need to spend some time and look at it.
Can spend some time at it. So.
I like your
Sir, I
honesty.
got everything except for the 2 over 3x.
3x cubed to the
Yeah.
this way. Yeah, I kind of figured. I was
Oh, I
expecting
got this up here though, but I never simplify it anymore.
you got this up here, so
Yeah.
mm-hmm.
I just leave it as a 3 over 2 and it. I
In the
never do
denominator.
anything else. Yeah.
Alright, so that means you got it right. All right, cool. All right, no problem. Dwayne, you got the x to the 6 over 6 done.
Yes, sir.
And everybody would have gotten that. This 3 over x is the same thing as 3x to the minus 1. Talk truth.
Yes, sir.
Come on. And remember, when we're integrating that, it's going to become 3 ln absolute value of x. See here? 3 ln the absolute value of x. You know, sometimes I put it there, sometimes I don't. And I need to change it and put it there because I'm talking about an indefinite integral. So let me correct my mishap right here. And copy. So just remember, when you don't have once you're talking about an indefinite integral, you need to have your absolute value sign. All right, so I've corrected my error. All right, so those two terms are not a problem. This one is not a problem either because I'm adding 1 to the power divided by the new power. So it's going to be 2x to the 4th over 4. See here? 2x to the 4th over 4. But I can simplify that. So I'm going to have 2 into itself 1 and 2 into 4 goes 2 times. I can just have negative x to the 4th over 2. See here? Same difference. Negative x to the 4th over 2. Or I can call it as negative a half x to the 4th. So it's the same difference. So this term is not bad. Neither is this term. This term. This term is also correct. You notice I said negative x to the 4th over 2. If I put this x to the 4th over here, so I'll get my negative x to the 4th over 2. Or I can choose to take it off. Whichever one. Same difference. Now, the last part is what I suspected would have given added. Matter of fact, everybody agrees with me for the first 3 parts?
Yes, sir.
Yes.
What about the business card? I'm just going to keep gets answering. What about the business card?
Yes, sir. Yes, sir. Fine.
Okay, man, I'll talk to me, man. Remember, you know, me let me want to see if you know me. I tell you the real truth. And I'm sure after this class, I'm just going to fall a good sleep. All right, but more want to keep me awake. If I could, let me just be real and confess something to you. When I got up, I said to myself, I said, Lord, if it was any other day, I just asked my classes to beg them for the day. Because I'm really not feeling good. And I said, no, if I do this, I am going to be behind even more than I was before. So I said, no, come on, snap out of it. And I'm giving thanks. It's now 10:30. And we have an hour and a half to go, and we're doing pretty well. Pretty well. So we are both making sacrifices this morning, and I'm going to ask that you just continue working with me, please, and we will get through this sojourn. All right. So remember, I said to you, let us just look at the last part. The last part is a troublesome one. Remember, I said to you that when you are differentiating, when you are given the root of x and you're asked to figure it out, the root of x is going to be the same thing as x raised to the 1/2 power. X raised to the 1/2 power. That's what it means. X raised to the 1/2 power. Now, when x is raised to the 1/2 power and we're integrating, we're adding 1 to the power and dividing by the new power. When we add 1 to a half, we then get 1/2, which is the same thing as 3/2. See here? 3/2. And divide by the new power. 3/2. This is untitled though. Really and truly, the integration ends here.
Sir.
Yes, Papa.
So when you say the square root of a half, sir, it gives you 3/2.
The square root of a half, when converted, is x to the 1/2 power.
Oh.
But when I integrate now, see this I note yourself? When I integrate x to the 1/2, remember the rule of integration says you add 1 to the power and divide by the new power.
Yes, sir.
So I'm adding 1 to the half, and then I'm going to divide by the result. I'm going to add 1 to the half, 1 plus a half is 1.5. Now 1.5 as an improper fraction is 3/2. So I'm going to add x to the 3/2 and then now divided by 3/2.
Okay.
Well, guess what now? Something that a lot of the teachers never did know. I doubted my teacher didn't tell me as well at school. The teacher said, invert and multiply. Why do you invert and multiply? Don't question me, boy. That's what the question goes. Invert and multiply. And that's what I was taught earlier on in my mathematical life. Some things that I wanted to explore, I had no time in class to explore it. We saw it go, that's the rule. We said, okay, it's a rule, it's a rule. But let me show about this now. When you have 3/2, and you want to get rid of this 3/2 here in the denominator, we have to multiply by its inverse. And that's why teachers used to say to you, invert and multiply. So in order to get rid of this 3/2, I have to multiply by the inverse of it. And the multiplication of the inverse of 3/2 is going to be 2/3. The opposite of 3/2 is 2/3. Let's invert it. All right? That's the inverse of it. So I'm multiplying not only the numerator by 2/3, but the denominator also by 2/3. Why, sir? Because when I multiply both numerator and denominator by the same number, I'm not changing the fraction. So I'm multiplying the numerator. First, I'm multiplying the denominator by 2/3. Why 2/3, sir? Because when I do this, it cancels out and gives me 1, and I'm left with 2/3 x to the 3/2. So this done here, so they work out to give me 1. That worked out to give me 1. So there's no denominator down here anymore. So I'm only left with 2/3 x to the 3 over 2. See here? 2/3 x to the 3 over 2 plus c. Done. Agreed?
Yes, sir.
All right. All right. Two more before I move into the definite integrals. So I'm giving you these two to do. That's question 4, and that's question 5. Start for it, please. I give you a couple of minutes, less than 10. Obviously.
Sir,
Mm-hmm.
check the chat.
Hmm. All right. Good, except that um, except that you left the answer as a negative power. Yeah, fully correct for the first one. With the strict continuous. Is what I'm saying, Jay? Junior?
Yes, sir.
Yeah, man. So fully right. Just do this conversion for me, honey. 9 x to the negative 1 as 1 over x, and you're good to go. Is everybody else okay with this one so far?
Sir, I didn't put that, sir.
Fair enough. Fair
So
enough.
I put 9 ln x.
9 ln x? No, remember. It's only when it is negative 1 the ln comes into play.
Oh, okay.
Yeah. Right, so So that's a teachable moment. So let me go again. Remember, guys, only when it is raised to the negative first power, you are going to use the ln function. Negative 2, negative 3, negative 4, any other negative number, it could to go. It is only when it is raised to the negative first power that the ln function comes into play. Always remember that.
Oh, sir, so you just integrated it normally. So you put the x squared in the numerator. Okay.
Very nice. And that's what I get for the other question. Check yours, Jay.
Sir, can go back up, please?
To which one, Kiss? Very good, Jay. To which one? You want to go back up to which one?
Number 4.
Mm-hmm.
Yes, sir, I got that for number 5.
Good job. Sit over here, Kiss. Kiss, are you okay now? Am I able to move?
Finished, sir.
All right, guys. We're moving into the definite integrals now. Very good. Andrahan, Dwayne, Damian.
Yes, sir.
Nice. Stolz.
Yes, sir. 1 point.
Nice, very nice. All right, so we're moving into the definite integrals. This should be a little easier for me to go through because the same rules governing the definite integrals are the same rules. Sorry, the same rules governing the indefinite integrals are the same rules that governs the definite integrals. Same rules that govern the definite integrals, the indefinite integrals, are the same rules that govern the definite integrals. Now, definitely, Excess Community College is located at 137 Mountain View Avenue. The indefinite integral would have told me to just, where's Excess Community College? Mountain View Avenue. No, I mean, I go to school because at Mountain View Avenue is volatile. Okay, not all sections of Mountain View Avenue is volatile. But it's a Mountain View, and there are very many sections of Mountain View. Okay, what is this actual address? 137. Oh, up at the top part of the song. Absolutely. Yeah, man, it's safe. Thank you. All right. So my definite integral is giving me something that is more specific to what I'm looking for. All right.
Sir, question.
Yes, Papi.
For the last answer, I got it correct, but I'm confirming something with you. For the x, the x plus c, I had 1 plus c. Would it still be correct? It's the same. It has to be x.
Yes, sir. That's the x. Because when you integrate 1, you get x.
Oh yeah. True.
It's not differentiating. So it's when you integrate 1, you get x.
It has to be x then. Okay, so, all right, so I understand.
Yeah, man. All right. So remember now, the definite integrals are worked in a similar fashion to the indefinite integrals. Real talk. The only difference to this is that it has now an upper limit and a lower limit. So if you look here, you see that my 3 is my upper limit and my 1 is my lower limit. My 3 is the upper limit and my 1 is the lower limit. So do me a favor. I'm not even going to show you what to do here. Just go ahead and just integrate this function for me, please. X cubed, x squared plus 3x plus 2. Do that for me, please. I'm going to step up to half a second. I need to go and do something. Integrate this for me, please. I'm going to finish integrating this. I'll be back within a half a minute. All right, I just walked out the sleep. I think I'm ready to go again. So be around with me. Remember, not 100. This week has been a rough week for me. Let's go. What is the integral of x squared plus 3x squared plus 2? Final answer is
X cubed over 3 plus 3x squared over 2 plus 2x plus c.
all right. Okay, thank you. Now, 99.99% correct. The difference with this one now, Tan, and the rest of you, is that because we're now in a definite integral, we're not going to put a plus c. All right? But you're correct. Because we're now doing a definite integral, we're not interested in having the plus c. So this is our integration. X cubed over 3 plus 3x squared over 2 plus 2x. So not putting a plus c because we know where excess of community college is. 137. Right? So we don't need to put a plus c. No, I have my upper limit as 3 and my lower limit as 1. Watch it. See here, so upper limit 3, lower limit 1. So the formulation is going to be my upper limit minus my lower limit. Upper limit minus my lower limit. So what do you mean by that? I'm going to substitute the upper limit into this function here. And then the result, I'm going to subtract that from there. I'm going to subtract the lower limit from that result. And I'm going to do the same thing here. So anywhere in the function I see x, I'm going to substitute 3. Watch it. 3x cubed over 3, see it here, so? Plus 3 times 3 squares over 2, see it right here, so? Plus 2 times 3, see it right here, so? And then I'm subtracting the lower limit from it now. So anywhere in the same function, I see x, I'm substituting my lower limit. 1 cubed over 3, see it right here, so? Plus 3 times 1 squared over 2, see it right here, so? Plus 2 times 1, see it right here, so? Every single time, the bigger number will be on top, and the smaller number will be at the bottom. Hence, upper and lower. There's no way I can have a smaller number up top here and a bigger number on the bottom here. That won't work. All right. Now, I'm evaluating. I'm evaluating 3 cubes. 3 times 3 is 9 times 3 is 27 over 3. 3 squares is 9 times 3 is 27 over 2. 2 times 3 is 6. 1 cube is 1 over 3. 1 squared is 1 times 3 is 3 over 2. 2 times 1 is 2. LCM here is 6. 3 into 6 goes 1 time, 2 times, and 2 times 27 is 64. 2 into 6 goes 3 times, and 3 times 27 is 81. There's a 1 over this 6, and 1 into 6 goes 6 times, and 6 times 6 is 36. Similarly, my LCM here is 6. Right here, 3 to 6 goes 2 times, and 2 times 1 is 2. 2 into 6 goes 3 times, and 3 times is 3 gives me 9. There's a 1 here, and 1 into 6 goes 6 times, and 6 times 2 is 12. So I can look at 12 here. 54 plus 81 is 135. 135 plus 36 is 171 over 6. Minus 2 plus 9 is 11. Plus 12 is 23 over 6. Once I'm adding two fractions and the denominators are the same, I put at the denominator and do the operation of the numerator. So this is going to be 171 minus 23, which is 148 over 6. I'm going to get 74 and 74 over 3 units squared. That's my answer. So you have up to here. What you now need to practice is the upper limit minus the lower limit, which is not difficult. Alternatively, no, I'm not going to do that. Same difference. All right, do me a favor. I'm giving you this now to do for me. Remember, the integration is what it is that we have been doing since morning. You know how to do the integration. Don't worry about it. The only thing now that I'm really wanting to develop in you now as a new topic is the substitution of the upper limit minus the lower limit. So I'm giving you 6 minutes, 2 minutes to do the integration, and 4 minutes to do the substitution of the upper limit and lower limits. So let me get your answer. Start now,
Sir,
please. Yes, only one, please.
sir, why we put the unit squared part?
Because we're calculating the area.
Oh,
When we calculate volume, it's going to be cube. It's calculating the area. Finish?
Sir, 3 more minutes.
Okay, cool.
Sir,
Yes, Jay.
check the chat.
Okay. Okay. Dwayne, Damian.
Finish, sir.
Okay. What you got?
37, Anna. Yeah, that.
Okay. Um, mm, we need to check Jay. What is happening here? Dwayne, Dana, Damian, Andrew Hunt, Shaquille, Laura, Tess, and then the rest of us. Did you get this for your integration? 4x to the 4 to the 4 minus 5x cubed over 3 plus 2x squared over 2 minus 1x?
Yes, sir.
Yes, sir.
Alright, good. So the integration is not a problem. The problem then is going to be the substitution for at least one student. Look at what it is that I have. I'm substituting the upper limit, so it's going to be 4 times. Sir, these are correct. So you couldn't cancel out. I couldn't cancel this. Yes, it can. It can. And I ended up doing it a little later on. So this is
Sir,
4.
so
Yes,
all
ma'am.
of it break it down, we're supposed to get the same answer same way.
Absolutely. 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 So this is 4 times 3 cubes, teacher, over 4 minus 5 times 3, rubbishness. 4 times 3 to the 4th over 4, minus 5 times 3 cubes over 3, plus 2 times 3 squares over 2, minus 1 times 3. Minus the lower limit is 2. So in the function, everywhere I see x, I put 2. 4 times 2 squares, 4 times 2 to the 4th, I'm sorry, over 4, minus 5 times 2 to the 3rd over 3, plus 2 times 2 squares over 2, minus 1 times 2. So that's my substitution. Then I'm going to evaluate it. These 4's cancel out. So I'm going to say 3 to the 4th. 3 to the 4th is 8 to 1. This is 3 times 3 is 9 times 3 is 27. So it's 5 times 27 over 3. Right here, so 3 squares is 9. So it's 2 times 9 over 2. But the 2's cancel, so I'm just left with a 9. Minus 1 times 3 is negative 3. Similarly, these 4's cancel out. So I'm just going to have 2 to the 4th. 2 to the 4th is 16. And 2/3 is 8. So they have 5 times 8 over 3. Right here. 2 2s is 4. 4 2s 8 over 2. Lie. These two cancel out. So I'm just going to have 2 2s 4. Minus 2. So it's 8 to 1. 3 into 27 was 9, and 9 times 5 is 45, so it's minus 45. Plus 9 minus 3 is 16. 5 is 40 over 3. 4 minus 2. 81 minus 45 is going to be 36. 36 plus 9 is 45. What am I saying?
So
Yeah,
36 plus 9
no,
is
I'm right.
45. Yes.
I'm right. It's 45. I did say 45. 36 plus 9 is 45. 45 minus 3 is 42. I just lost my sprint of thought. So 81 minus 45 is going to be 36. And 36 plus 9 is 45. And 45 minus 3 is 42. 16 plus 4 is 20, minus 2 is 18. 18 minus 40 over 3 is going to give me 40 thirds. And that is going to give me 112 over.
So how you get the 112 over 3?
42 minus 14 over 3.
Yeah, but I'm still not get it, sir.
Jay, you know that you are correct? Because 3 into 3 was 1 time. No, you're
Sir,
not correct, you know.
sir, remember telling you. So, I'll make mistakes. So, for the lower limit, me put 1. I'll put 1.
Oh, okay.
And then I never put I did have 4x cubed plus 3 plus 5x squared instead of 4x cubed minus 5x squared. So that
That's a problem. All right. I'm happy to fix it.
Sir,
All right. Yes, please.
I'm not getting no 112 over 3.
You have a calculator with you, kids?
Repeat, sir.
You have a calculator with you?
Yes, sir.
Can you turn it off and then turn it back on for me, please?
Repeat.
Turn it off and then turn it back on for me, please.
Yes, sir.
Can you put in 42 for me?
Yes, sir.
Minus,
Yes, sir.
open brackets,
Yes, sir.
14.
Yes, sir.
Look to the top left hand corner, you see the ABC button.
Yes, sir.
Press it and then press 3.
Yes, sir.
Close the brackets.
Yes, sir.
Press equal or answer. Automatically. Are you seeing 112?
57 and 1 over 3.
Do you see it?
57 and 1 over 3.
57
And 1 over 3. No, wait. If because, sir, like, we just realized 37 and 1 over 3, but is it true one of the black thing is not there? I don't know if it's a 5 or a 3.
Oh, so it's not me then, it's a calculator. All right, so that's how you get it on. Somehow, I feel like some of you have gone asleep. Iscal, are you with me?
Yes, sir.
Yes, sir. Yeah.
Oh, okay. Looks like I'm gonna go and sleep, man. So when you find the area, it's really gonna be area square. All right, I'll give you another one. Remember, sorry, this one looks very similar to the one that we did before when we were looking at the indefinite integral. Except, you're supposed to see what is going to happen. I want you to work on that, please.
Sure, the lower limit is what? One that I can scroll up a little.
Negative 1.
The lower limit.
The lower limit is negative 1, right?
I'm not seeing it. Yes. Okay.
Oh no, I didn't want you to see that. That's why I never carried up in a jar. The way make me just all right, there you go, the way. You can't see it no pops.
Yes, sir. Yes, sir.
All right, bless up. Start with these, all of you. All right. Finish the integration. Finish the question rather.
3 more minutes.
All right. All right, your 3 minutes are up now. What's the answer?
5 and 1/3.
5 and 1/3. Anybody else? Talk to me, guys. I have 20 of you here. Waiting, guys. Waiting. Want to drop a seat, you know? Because I have to change position because of how I'm feeling. So don't let me drop a seat. Talk to me.
I'm gonna get 22.
You get 22. All right, fair enough. So I hear 5 and I get 22. I need 2 other people to answer me.
Sorry, I got 24.
Okay, one other person.
-1.
-1. I get 16/3. Let me just
Oh, sir, I didn't change the sign.
did you divide through, guys, by the x for every term in the numerator?
Yes, sir.
All right, good. And did you recognize that you're going to have 11 over x so that when you integrate, you can get ln 11 ln x?
Yes, sir.
Good job. That's the only trick to it because everything else I know you know how to do it. Now, ln1 is equal to 0. ln1 is equal to 0. And remember, so this is where it comes into play now, because I want all of you to look at this. Remember, go back to here. My head hurts now. Jesus. We're gonna go right here, 11 ln x, what is the absolute value of x? The absolute value of x. Remember, I said to you that you can't take the logarithm of a negative number. Here goes a negative number. So I have to use the absolute value of x. So this is where the absolute value sign becomes very critical now. Because when I take the absolute value of -1, I'm not taking the logarithm of -1 number because I can't take the logarithm of a negative number. But when I take the absolute value of -1, it's really taking the absolute value of 1. The absolute value of 1 is 0, so that's why that goes to 0 also. So it's going to be 5 over 3 plus minus 1 over 2 plus 1. Yeah. Go ahead, I'm hearing you. Talk to me, please. All right, I don't know if anybody's hearing what she's saying, but I'm not.
Our connection is off, sir.
Oh, our connection is off, right. I'm not hearing you, honey. Who was that? Was that Javier?
Yes, sir.
Yeah, all right. All right, JJ, your connectivity is poor. Send me a message, not to the not to the phone that has no microphone. I just log on there as a backup in the event that this one goes. I don't lose connectivity for the class, as I normally do. So send me a chat to the one that I'm sharing from. All right, so I'm gonna have 1 cube is 1 times 5 is 5, 5 over 3 here. 1 squared is 1 over 2, so I'm gonna have minus 1 over 2, and this plus 1 is gonna carry down to here. I'm gonna have negative 1 cube is negative 1 times 5 is negative 5 over 3 here. And then I'm going to have negative 1 squared is positive 1 over 2, negative 1 over 2, right here. And this is going to be negative 1. And then my LCM is going to be 6. My LCM is going to be 6. 26 goes 2 times, and 2 times 10. 26 goes 3 times, and 3 times negative 1 is negative 3. 196 goes 6 times, and 6 times 1 is 6. LCM again is 6. 26 goes 2 times. 2 times negative 5 is negative 10. 2 into 6 goes 3 times. 3 times negative 1 is negative 3. 1 to 6 goes 1, and 1 times negative 6 is negative 6. 10 minus 3, 7 plus 6 is 13 over 3. And negative 10 minus 6 minus 3 is negative 19 over 6. Once I have the denominators with the same number, I put it back and do the operation for the numerator, which is 13 minus 9 becomes 13 plus 9. So that's 20, 32. So it's 32 over 6, which is the same thing as 16 over 3.
Okay. I had written 5 and 1/3 as my final answer.
No man, 5 and 1/3 are the good up answer, man. The bright people them write the answer like that.
Sir, I want to ask a question. The one that is the 11, 1, n 1, I have the bracket, the one in the bracket, or it turned to 0.
Take out your calculator again for me and put 11. Then press the ln function. It's supposed to be in the middle of the calculator. And then press 1 for me. And then press equal and what you get.
Okay, sir.
Ln one of a function is always 0. And ln of a negative number is always on the side. Math error. And that's our answer. 5 and 1/3. It's cube. All right. How are you feeling?
Good, sir.
Can I take a break from there? I'll just touch upon something else here. Because I mean, I'm going to send all of these to you, so you can go ahead and do it. It's the same thing over and over that we're doing. The integral of an indefinite function, the integral of a definite function. But what I want to look at now is the integration of the exponential function. There are only 2 of them.
Yes, sir.
And all right, thank you, sir. There are only 2 of them, and just 2 rules that we need to know. One of them I've already told you about. The integral in the rules. The integral of an exponential function is the exponential function itself. You're going to differentiate the function and then reciprocate it plus c, and your answer done. Let me say that again. What page number at? Page 15. Rule 5. The differential of the exponential function is the exponential function itself, except that I'm integrating the function up top, reciprocating it. So the integral, the differential of, even though I'm integrating, I'm going to be differentiating the function. When I differentiate the function up top, I'm then going to integrate it. Rubbish. I'm going to differentiate it and then reciprocate it. So even though I'm doing an integral, so the integration of an exponential function, e to the ax dx, is going to be 1 over a ln e times e to the ax plus c. E to the ax dx is going to be equals to 1 over a e to the ax, because ln e is equals to 1. If I'm in ln of this, so I don't normally tell you that this piece here. All I just tell you a while ago is once it is that is the exponential function, once it is that is e, once it's the e, I integrating the integral of e to the ax dx, see to the answer to e to the ax. All you're doing is differentiating ax. So when you differentiate ax, you're going to get a. When you differentiate ax, you're going to get a. I'm going to get a, you're reciprocating, so you have 1 over a. So your answer is going to be 1 over a e to the ax plus c. Talk truth.
Sorry, I can go over that again, please.
The integral of a of e a to the x dx. The integral of a. The integral of e. The integral of e a to the x dx is going to be e a to the x, here e a to the x, then I'm going to differentiate a to the x, I'm going to get a, and then I'm reciprocating it, I'm going to get 1 over a. So I'm going to get 1 over a e to the ax plus c. The integral of e a to the x is going to be e a to the x. The integral of e to the x is e to the x. Just like when I did differentiation and I said the differential of e to the x is e to the x, the integral of e to the x is the integral of e to the x is e to the x. So in the integration let me give you, you can write it back as e to the x, whatever x is. And then I'm going to differentiate the power. When I differentiate ax, I'm going to get a. I'm going to get a. When I get a, I'm going to get when I get a, I'm going to get 1 over a because I'm reciprocating it. You may be wondering, sorry, then why did you have this thing in blue? All right, let me explain this thing in blue. Because I'm going to find ln of e. I'm going to find ln of e, but ln of e is 1, so I just went ahead straight and just ignore it. Let me jump to number 2, and then you can appreciate why I put the ln e there. If they give you the integral of a b to the x, if they give you the integral of a b to the x, the integral of a b to the x dx, it's going to be 1 over b, just like how I had this as 1 over a, 1 over b, ln a. I have to find ln of that function. But ln a is not equals to 1. Ln a is going to be equals to a different number. So it's going to be ln a. The same integral of a to the x is going to be a to the x. So it is a to the bx plus c. So once you differentiate it, once you integrate in an exponential function, it's going to be the exponential function itself, but it is what you do with the function. All right. So what I'm saying to you, ln a is not going to be equals to 0 or equals to 1. I'm sorry. You know that a can't be equals to 0, and a is not equals to 1 for reasons that we already discussed. So I'm saying to you, if you were to give that, given this, a to the bx, that's what you're going to do. Let me jump into the question. If I ask you to integrate e to the 2x, you can write back e to the 2x. See it right here, sir? Well, you can differentiate the function up here. The differential of 2x is going to be 2. You put 1 over 2 plus c. See that?
Yes, sir.
Sir, do that again, please.
The integral of e to the 2x. The integral of e to the 2x is e to the 2x. The integral of any exponential function, you can write by the exponential function, but you're going to differentiate the function and reciprocate it. So the integral of e to the 2x is going to be e to the 2x plus c, but I have to multiply that now by the differential. I have to differentiate the power, and the differential of 2x is 2. And then I now need to reciprocate 2, and I'm going to get a half. So it now becomes a half e to the 2x plus c.
Okay.
See that?
Yes, sir.
All right, let us look at this one here. Let me just run through these with you. This one is e to the x squared plus 5x plus 2. Not a problem. Don't look at it and say, Sir Hardy, no, I'm following the same rules. When I'm integrating an exponential function, is the exponential function itself. So I know that piece of my answer is going to include e to the x squared plus 5x plus 2 plus c. But I now need to differentiate the power. When I differentiate the power, what do I get? Differentiate x squared plus 5x plus 2 and tell me what to get.
2x plus 5.
So it's going to be 1 over 2x plus 5, e to all of that something. Tell me if you've seen it now.
Yes,
I'm
sir.
done. Yeah, man. So all I'm doing, Damien, all I'm doing is differentiating the function, reciprocating it, multiplying it by the rest of the answer. Good to go. Laura, test.
Answer.
Okay. Now, life is not always black and white, black or white. There are sometimes shades of gray, many and varied shades too. All right, let's go. So I'm going to be using this as a refresher to get you to do your differential of a quotient. I want you to differentiate x plus 1 over x minus 1. X minus 1 over x plus 1 for me, please, using the quotient rule. X minus 1 over x plus 1 for me, please. Start for me, please, guys.
Is it 0, sir?
0 when you differentiate the x minus 1 over x plus 1?
Yes, sir.
No, I didn't get 0. Anybody else got something else? I didn't get 0. Remember, it's the denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Traffic influence, please. Denominator.
I leave out the square, sir.
Okay, that's a problem. So it's the denominator times the differentiation of the numerator minus the numerator times the differentiation of the denominator all over the denominator squares. Excuse me. Everybody is reminded now of the differentiation of the quotient 2 over x plus 1 all squares.
Oh, sir, I forgot that the x could be cancelled. But I would have gotten that.
All right. I'm gonna end here. So you guys, I'm gonna have a terrible headache now. I'm gonna end here. I'm gonna see if I can get a little rest and then I send off the document for you. And I'm gonna see if I can purge this the recording I send off also. All right. Thanks for coming out.
Okay, sir.
Okay.
Yes, sir.
Good man.